Hi, welcome to Service Mesh 101. My name is Spike Curtis, and I am a senior software engineer at Tigera. What we're going to do today is talk about service meshes, but not talk about any particular service mesh, just kind of give an overview of the space and what they do. So to that end, we're going to start with a recap of service-oriented architectures, which is kind of the motivating reason or the areas where you might consider using a service mesh. Then we're going to talk specifically about, once you're in a service-oriented architecture, why you might want to use a service mesh. Then we'll talk about what a service mesh is and how it works. And then to illustrate some things that service meshes can do that are very difficult in other techniques, we're going to talk about one specific advanced use case, which is traffic management. All right, so let's dive in. So first I want to give you just a kind of recap of what we mean by service-oriented architecture, because that's going to be the sort of substrate on which we're going to frame all the rest of our discussions about service mesh. So if you think about what service-oriented architecture is, it's usually presented as a way of building applications that are available over the network, and you contrast it against what we sort of retrospectively call monolithic architectures. So over on the left is a typical monolithic architecture. You see that we have clients. They come into our application usually over the internet, but it could be some other network, maybe a private corporate LAN if this is a private application. But clients are coming in. And typically, the application or the number of clients is so big that it would overwhelm a single instance of the application. So we have multiple instances of the application serving that traffic, and we use a load balancer to balance the load among all those different applications. So traffic comes in, the load balancer chooses a particular instance of the application to send it to, and that one serves the request that the client made. Now, typically we have separate from the application logic a persistence layer at the bottom, and that'll continue to be the case even in service-oriented architectures. And the persistence layer is where we keep all the data that persists, all the non-volatile information. So user profiles, their messages, anything that the user keeps in the application. And that could be a database like Postgres or MySQL. It could be a cloud database like Mongo or Elasticsearch, or any number of kind of different persistent layer stores. But the application logic is sort of reaching out to that to actually get the information that it needs. It might be caching it. So we contrast that to what's going on with a service-oriented architecture. And from the top, this looks pretty similar, right? We have clients, they come in, they hit a load balancer, but instead of hitting a single monolithic instance of the application, we actually separate out some of the different things that the application does into what we call different services. So I have these labeled just with letters. Presumably you would choose names that were more appropriate to your application. But the load balancer is now understanding what the user is trying to do by looking at their request and directing it to a service that fulfills it. So these are usually arranged around either customer experiences or the way that the application works kind of architecturally might make up a different service. And the reason that we go to service-oriented architectures is kind of mainly twofold, and they both have to do with scale. One is about the application scale itself. You will often find in building an application that different things the users try to do happen at different rates as you scale up. So for example, like let's say I'm a microblogging platform like Twitter. Users are going to be requesting tweets on their timeline all the time. And they're comparatively much more rarely looking at their own profile, looking at other users' profiles, or editing their profiles, right? Tweets is the lifeblood of what's going on. I need a lot of capacity to serve up tweets. I need very little capacity to serve up user profiles, relatively speaking. If I had a monolithic application, I would have to turn up both of those things at the same time because I only have one knob, the number of instances of the application. When you break up your application into different services, you can now scale them independently. And that's very important for going to very high scale applications. The other kind of scale dimension here is not end user or traffic scale, but organization scale. when you have a lot of developers working on your application, if they are all touching the same piece of code with your monolithic application, that can become very painful, right? You have change requests all coming in. You want to be able to kind of separate out concerns and control who is in control of what, and that can be very difficult when you have everything all in one chunk of code that gets built. So breaking these up into different services allow you to have different teams working on the services, and you define APIs, which are the contracts between the services, and that allows these guys to operate with some independence. As long as they don't break the contract of what the other services are depending on, they are free to make whatever changes they want to the application, and can even roll those out independently, right? You can have an upgrade to Service D that happens without Service B or Service C necessarily being aware of that or even really caring. Okay, so some more terminology about service-oriented architectures. This edge load balancer, in the monolithic case, all it had to do was look at maybe connections and redirect those to the application. But here, because there are different services, and these guys really are not equivalent, the edge load balancer needs to understand something about the application in order to figure out which backend it's going to send it to. So in that case, we talk about these things being either an application load balancer, or ones that have even more functionality to sort of manage the APIs that are presented to the end user are called API gateways. The other thing to think about is the number of services in your call graph. The width of it is basically how many services are sort of end user facing. In this case, I have 3 of them that are kind of coming from this edge load balancer. And the depth is how many calls deep you get before you're at the bottom of your service graph. So the call that causes the most things to happen in series is the one that's deepest in your graph. And so this kind of allows us to talk about another term that gets kicked around a lot, which is microservice architectures. And microservices really are just a particular service-oriented architecture, a particular way of doing service-oriented architectures. And in microservices, you emphasize creating a lot of very simple services rather than a few kind of larger or more complicated services. So the idea behind a microservice is that you separate things out into really small pieces of functionality that are easy to explain, easy to describe, and easy to have a team work on. And the other thing that you often do in microservice architectures is emphasize width over depth. So if you were to emphasize depth, then what can happen is, because these services have to call each other, that can create latency in each one of these hops, and each service doing the processing, meaning that your application doesn't feel as fast. So if you emphasize width and have the services arranged around customer experiences, so services might be around doing your shopping, and then you might have a completely different service that's the card, and a completely different service that's the payment, things like that. If you arrange your services around what the customer is trying to do, then you can keep your call graph not very deep and as a consequence very wide, and that improves performance or improves latency for your customers. So that's what we mean when we talk about microservices. It's just a certain kind of service-oriented architecture. Okay, so this is kind of going to be our canonical example that we're going to use to explain why you might want a service mesh. Okay, so remember, we still have clients connecting in through the internet through this load balancer, and when you run applications in production, sometimes they break. So if clients are starting to see errors coming in to their application, hopefully you have some way to detect that clients are actually seeing errors. And your job is to figure out, well, what's broken in my application? How do I fix this error that the clients are seeing? And if you have a microservices architecture, you might be able to correlate what kinds of things are breaking to a particular service, right? Because these services are arranged around customer experiences, so if just one of your experiences is broken, then that can help you narrow down to what service it is. But even if I narrow this down, right, I know that the experience that service B is providing is broken. Does that mean that service B itself is broken, or is it that the call upstream to service D is breaking? Is service D itself breaking, or is service D's connection to the persistence layer breaking? I have to answer all of these kind of questions in order to be able to find a root cause and have some hope of fixing this. And this is very tricky in microservices applications, especially when the number of microservices get really large, dozens or hundreds that you see in these really large applications in companies these days. So what we have sort of developed to help operators and developers solve these problems is what we kind of broadly class as observability. And when we talk about observability, we usually mean a couple of different things. One is logging, right? Each of the services is going to be producing logs that make sense to tell about what's going on in it in sort of real time. And in order for those logs to be useful, operators and or developers need to be able to get access to them. So you need to be able to pull them out of the service themselves, store them somewhere where your actual human operators and human developers can make use of them. The other thing is statistics and metrics. So services can be keeping information about what's going on in them, how healthy they are. And so you want to look for metrics that are good proxies for whether or not the service is performing well. So number of requests that it's performing per second, latencies, how much memory is it using, things like that. And then lastly, we talk about tracing. So what a trace is we look at a single request that an end user makes into the application, and we follow that request through the service graph. So we see it hits one service, and then maybe that triggers a call to some other services, and we actually follow that all the way through. So a trace is about looking at one specific call and being able to see the full information of what happened with that and where failures occurred. Now, because we typically have a lot of calls into our application, we won't be able to store traces for every single application. That would be a huge amount of data. So typically tracing is done with some sort of sampling rate. So you get a certain number of requests that come in that you actually keep a trace for. And these three guys, logging, metrics, and tracing, are nominally the sort of holy trinity of observability. This is what everyone is going to kind of propose to you as the solution for being able to observe what's going on in your application. We also sometimes refer to this not as observability, which is the sort of end goal, but telemetry, which is the sort of solution to that. So when people talk about observability or telemetry, really they're probably talking about logging, metrics, tracing. Okay, so that's one area of sort of pain with running a service-oriented architecture, and what we do to make that pain less. The other thing that you have to deal with when you have a service-oriented architecture is understand that you have multiple instances of a lot of these services. So for example, on this diagram, I've got 2 instances of service D. So that means that when any of these other services are calling in to try and get a request into service D, they need to understand that there are 2 instances. They need to sort of understand what the addresses of those instances are that they can reach, and they have to be able to think about how they're going to load balance across those services. And you still probably will have multiple instances of most of your services, either for availability concerns if one of them dies, or for scale concerns. So being able to deal with that sort of service discovery and load balancing is a basic requirement, basic feature of distributed systems. The other thing that we often have to worry about, especially in microservices architectures, is how emergent behaviors of the system manifest themselves in the face of errors. So we're connecting these services over a network, and the networks are not always reliable. The services themselves may not be reliable. What happens when one of them fails? We need to be able to be resilient to individual failures in the application, because we've sort of multiplied the number of different things in the application. If we depended on them all operating error-free, our chance of doing that goes lower and lower as we add more things. So one of the things that you can do to deal with or to have a resiliency is to add retries, right? If the network fails one of your requests, you can retry it. Or if you have multiple instances of a service, if one of them fails, you can retry it on another one. But you have to be careful about introducing these sort of primitives, because if you just sort of naively add 3 retries to every RPC, you could inadvertently triple the number of requests in your network during a failure. So you have to have other techniques that sort of mitigate the possibility of retries and sort of have a system that is overall resilient. So people have thought about this kind of stuff. They've built libraries that handle these kind of things. So the common techniques are things like circuit breaking. So when a backend starts having too many failures, you just stop using it entirely so you don't overwhelm it with more traffic and more retries. Health checking, so you're proactively trying to figure out which backends are healthy and are going to be able to respond to your request, and kicking out the ones that aren't. Timeouts, other kinds of resiliency features are going to be part of a distributed system that works well and is highly available even in the face of small failures. The last thing, or the last big category to think about in terms of service-oriented architecture networking is controlling what can talk to what. So for example, if I have an application running in a cluster and a developer spins up a new copy or new version of Service 1 that they want to develop on, they want to see how it behaves. This thing might be configured. The developer might have accidentally configured this guy to talk to production copies of Service D and production copies of my database. And typically, I don't want that to happen as a developer, right? The developer is actually on this machine. They're seeing the data, and you don't want your developers to be accidentally seeing live data from your end customers, because that invades their privacy. It might break laws. There are all kinds of reasons why you may not want this to ever happen in terms of a live developer. So this was an innocent mistake, and I want to have some way to have my my application networking know not to allow this to happen. But there may be malicious things happening as well as innocent mistakes. So if you have an application that's connected to the internet, you are going to have people trying to come in and take over that application and do harm to your business or to your users. So imagine, that a hacker finds some weakness in one of my services, right? They find some unpatched vulnerability in service I. Maybe it was never previously disclosed, or maybe I hadn't patched it yet, but service I now becomes compromised by the hacker. I don't want to depend on defenses that just completely crumble as soon as a single one of these microservices is compromised. There's a lot of them. The probability of finding vulnerabilities in them, nominally is going to go up as I have more and more services. So I need to have a defense strategy that is resilient to one of these things crumbling. And so if I just am allowing all network connections, an attacker might take over service I and use it as a base of operations to attack other services. Or they might attack the persistence layer directly, which is typically kind of what their end goal is to either exfiltrate customer data, which they can then exploit, or lock it up with crypto and ransom it back to you. So we need to have a method of keeping our network connections secure inside a microservices architecture, because we have so many more network connections. These things are using the network in a way that a monolithic application never would have. So the techniques that we have for keeping those connections secure are, broadly speaking, identity, being able to figure out who is on the other end of a networking connection; authentication, being able to prove who you are on the other end of a connection. So the identity is sort of figuring out like how I identify different participants in the network. I identify other microservices. Authentication, what is the mechanism that I actually prove that identity? Authorization, so once I know who I'm talking to, I have to answer the question of should they be allowed to do what they are doing, right? Should they be able to access customer sensitive data or not? And then lastly, auditing, keeping track of what happened. In case something bad does happen, you can then have a trail to figure out what the extent of your breaches are, and then what your responsibilities are to your customers or to your regulatory environments to actually be able to deal with the aftermath of that. Okay, so we've talked about three kind of broad classes of things that you need to take care of in terms of service-oriented architectures. And so sort of broadly speaking, these are exactly the reasons to have a service mesh. Service meshes are kind of a uniform way of being able to tackle one or more of these problems. Now, not all service meshes solve all of these problems, but generally speaking, service meshes are going to be trying to help you solve at least one, probably multiple of these problems in a uniform way across your applications. So the thing to think about here is not so much which one of these problems do I have right now, but what is the way that I want to kind of build my application to tackle this stuff in the future? Because if your application is successful and continues to grow and continues to become more functional and more complicated, even if you don't have all of these problems today, you will at some point in the future. So thinking about service meshes as a strategic investment is a good way to sort of frame this as a way that you can not only solve whatever particular challenges are up against you today, but also maybe get ahead of some of these other challenges that you know you will have down the road. All right, so let's talk about what a service mesh is and how it can actually help you with those three classes of problems. All right, so the kind of state of service-oriented architectures today is that in most organizations, developers want to choose different tools, different frameworks, different languages to write the different services. They want to pick the ones that best match their skill set or best match the problem set that they're trying to solve. So in a lot of organizations, these applications are made up of different frameworks and things. So Service E might be written in Python, Service F might be in Ruby, Service D might be in Java, Service I might be written in Go, and etc. Or even if they're written in the same language, they might use different frameworks, right? This one might be Flask, and even if this one's Python, it might be written in Django or something like that. So you want to be able to be responsive to those needs of developers if you're a platform owner, and so trying to solve these problems of service-oriented architectures around distributed systems and resiliency, around observability, and around security means that you have to have software that does that. So if you try and build those functions into the services themselves, you may find yourself having to do it multiple times for different frameworks and languages. And that typically leads to having very inconsistent results around what is supported and what isn't, and what quality these different frameworks and languages are at in terms of what kind of observability, what kind of tracing, what kind of resiliency features. In the worst case, you can have things where the set of features and the set of kind of resiliency doesn't overlap, right? Where the framework that you're using to secure Service F doesn't know how to talk to the database in a secure way, and then you're spending a lot of resources kind of building these things up. So one way to deal with this is to just enforce consistency across your environment. Say everybody has to write in the same framework, everybody has to write in the same language, or the same small number of languages. And in some environments that can work all right. And you might have enough kind of engineering resource to build the right frameworks for the languages that are needed. If you look at a company like Google, there are 5 or 6 different languages that are the sort of languages that are sort of blessed to build services in, and there are good language frameworks for communication in each one of those 5 or 6 different languages. However, most organizations don't have the resources to develop that kind of stuff and maintain it, and are stuck kind of rolling their own things for different language frameworks. So service meshes attempt to simplify this picture by taking the solutions to all of those networking issues, right? The observability, the resiliency, and the security, and moving them out of the application frameworks themselves. So if you consider just two services and what sort of happens with respect to the network, is, you'll have a request coming into service B. Service B will do some work on that request. Maybe it will decide that in order to fulfill the request it got, it needs to make a subsequent call to service D. And then service D might be calling upstream, or it may be, the place that just returns the information back. So right now in this picture, service B is directly interacting with service D. And so service B and service D need to know who each other are. They need to know how to communicate with one another. They need to have all the logic to do the networking right. In a service mesh, what we do is we delegate all of that information about using the network to a proxy that is running next to that service. So all of the network interactions are to the proxy. So the service never talks directly across the network. It talks to its local proxy. And the proxies are the ones that talk across the network. And they talk not to other services, they talk to other proxies. So you get this proxy-to-proxy communication, and then the services talk with their local proxy. And this is sometimes called a service proxy or a sidecar proxy, sort of depending on who you talk to, but the architecture is the same. You're delegating the networking functions to the proxy. Now, the proxy needs a lot of information, a lot of runtime information about what's going on in order to do its job correctly, right? It needs to know what service D is, what IP address is, how many instances of service D, which ones are healthy. It needs to know the configuration about, like, how many times should I retry, at what point should I cut the connection, should I be encrypting, if so, with what keys. All of that runtime information needs to go in the proxy. And so what we do is attach the proxies to what we call a service mesh controller. Sometimes this is called a control plane, but the idea is the same, is that the proxies have a connection to a centralized place where we're managing all the runtime config of all the proxies. So the proxies this proxy on service B will then find out from the controller the existence of service D and all the different instances of service D and what their IP addresses are. And service D will find out about service B and what's the identity of service B when it makes this connection, and etc. So in this kind of architecture, these services don't need to care anymore about those detailed bits of networking. They can just concern themselves with the sort of business problem that they're trying to solve, and you move all of this network complexity into the proxy and then into the controller itself. So operators of the application or of the platform go in and adjust the controller in order to configure the networking that happens. And typically the service mesh controller is integrated into the cluster management itself. So in this case, I've shown Kubernetes here. So these microservices would be running in pods in Kubernetes, but it could be any number of things, right? This could be AWS, and the controller is talking to the rest of AWS to find out about VMs that are being spun up or taken down. So that's the kind of service mesh architecture in a nutshell, and all of the things that are calling themselves service meshes basically share this. All right. So the last thing I want to do is give you an example, a specific example of something that service meshes can do that it's really hard to do in other cases. So one of the kind of big reasons to think about service mesh is to be able to tackle multiple of these problems in one go and manage it all centrally. But that can often be a little bit abstract in terms of, like, what am I actually getting here that I couldn't do before, besides just kind of consistency. And traffic management is a good example of these sort of advanced capabilities that service meshes can give you that are really difficult. So imagine, I'm back to my microservices diagram here, and I've labeled one of these services users. So imagine that there's this user service, and all these other guys are clients of the user service, and they need to talk to it. And so this is a messaging application. So the user's microservice is going to be responsible for figuring out what messages a particular user has, and also showing user profiles. So it has two different jobs. And when I originally designed this application, that seemed to make sense to put those two things together. But now, as I've grown, the number of messages and message API calls has grown at an incredible rate compared to the number of profile calls. So I, as an application developer, decide that I actually want to split up the user's microservice into two other services so I can scale them independently. Right? I want to go from one user service to a user message service and a user profile service. Now, without a service mesh, what I would have to do in order to make that happen is not only launch these two new services, but then go in after these guys are launched and edit all these other services, right? I have to edit service B so that before, when it called users slash message, it should be calling a whole new service, the user message service. And before, when it called user's profile, to get a user's profile, it has to talk to a new service called user profile. And this can be pretty painful if all of these different services are managed by different teams, right? If I'm the one managing the user service, I do my job. I refactor my service. But now I have another job to go out and talk to other teams and convince them to edit their code so that their code now uses my new service and things can be happy. So that could be really quite difficult in organizations and very time consuming. But if I have a service mesh, then I can program the proxies that are handling this network communication to understand what happened here. Right, that when service B, when the application code in service B makes a call to the user service and starts calling message APIs, that it should just redirect that to the user message service here. And when the service starts making profile API calls, it should redirect to the user profile service. So I can do that transparently without code changes on behalf of all of these other services, and that can be really powerful. It can sort of free your developers from having to convince other developers to change their code, because one of the things that's so great about microservices is defining these contracts, these APIs about how things communicate. But the downside is that when you want to change those APIs, it can be really painful, and so service meshes can give you that sort of best of both worlds, where you can define these APIs and actually keep them around, even though you're sort of changing what's going on under the covers. And this is the kind of thing that was available up at these edge load balancers in what's called API management or API gateways, but was really expensive to do everywhere inside the mesh. But by virtue of going to a service mesh, I now have these new capabilities on literally every connection inside the mesh can be adjusted in this way. All right. So that's just kind of a quick preview of an advanced use case for service meshes. And I will leave you with a set of links. Like I said, this is an overview of service mesh architectures in general, and I didn't want to talk about any specific ones other than at the end to mention, here's some places to go look to get some more information about particular service meshes. So Istio is a kind of full service mesh. It covers all those use cases that I just described, and it is using Envoy as the proxy. So Istio is a set of controllers with a slightly modified Envoy as the proxy for actually doing the moving the data around. Linkerd2 is also a kind of full-featured service mesh and uses basically the Linkerd is the name of both the controller and the proxy. So it's kind of a full-featured, fully integrated service mesh. Console Connect is a service mesh that is based on HashiCorp Console, and it's focused primarily on service discovery and security use cases. Aspen Mesh is a kind of full-featured service mesh made proprietary rather than an open source project like Istio. AWS App Mesh is a service mesh that's specifically designed to run in Amazon's clusters and also uses Envoy as the proxy. All right, like I said, this is not an exhaustive list, but should give you a good starting place from which you will find, more information probably than you require about different kinds of service meshes that are out there and are interesting to look at. All right, so that is all I have, and thank you very much for listening.